Hi folks, how are you? I hope you had a great weekend. If you can hear me, please like my comment, the message I left in the conversation chat. I don't know if you can see it or not. Yeah, please. Can you see it now? Okay, thank you so much. So as mentioned, I hope you had a great weekend. So today we are going to continue with the instructions of LegV8 assembly language. So as always, remember that part of the slides are taken from the book and its companion material. Today, the outline is very simple, procedure calls. We are going to see this element, which is very important and also very, very powerful. We could, what we call procedure is also what we refer to in other programming languages like C or Java's functions. So a procedure in LegV8 or in assembly language, it's a similar term for function. It's basically a subroutine that do a specific task or do something that maybe we are going to repeat at some place. It's mainly used as functions instead of having all my code in a main function. It's a good programming technique to have a program structure, and if I can divide my program in different functions, it increases its readability and so on. So, and it's also, if I have if I create procedures of functions which can be useful for other programs, it allows me also to reuse that code, increasing also my productivity. So for instance, let's see here an example. Imagine we have a procedure or a function which just swaps two values. So I will have, in a procedure, I will have the same as with a function. I will have some input data, some input variables, and in this case I have two variables, f and g, which are the ones I'm going to swap. And then the output, once I call that procedure, will be the variables with the values swaps. Okay. So if we want to write a procedure or a function in assembly code, so first of all, we are going to see how we do this in a high-level programming language. This is something similar what we do to C or similar languages. So we have, let's say we have the two input variables, which are f and g, and we have a procedure or a function which is called swap, right? So the input arguments for that swap function in this case are f and g. So then at this point, my program will jump to a place where this procedure is declared. In this case, we see it is the case here, and then in this procedure we just swap the values. I'm not interested in how those values are swapped, and I return the control to the caller. So then my program continues from after the making the call. Okay. So I think it's clear. I'm going to repeat this again. So I have two values. I just call a procedure which is going to swap those values. I go to the procedure, I do what I need to do, and then return the value to the caller, and then my program continues. This is as in any other programming language. So what we need to do in order to call a procedure in LegV8 or in assembly language or in ARMv8? So first of all, we need to place the input parameters. Remember that in the swap function we had two input parameters in registers from 0 to 7. Why registers 0 to 7? Because it has been decided that those registers must be used for arguments for procedures and functions. And how do we know that those registers are intended for that? Because remember, I told you that in the LinkBI reference data that you can find on Canvas, we have here a summary of the registers, and we see here that registers 0 to 7 are used for arguments to procedures and also for storing sending the results back. I have also placed on Canvas another document which maybe is more useful than this, more clear than this, for the registers. It's similar to this one. Okay, and here you can see clearly what I'm mentioning. Okay, apart from here, you have also this information on the slides from today. So then, once we have placed the parameters, the input parameters for the function or the procedure in any of those registers, what do we need to do? So we call the procedure. We call, following the example before, the swap procedure. Then if we need, we are going to see this later, if we need extra space, we also need to manage that extra space for our procedure. Then we do what we need to do. In the previous example, the operation was swapping the two values, and then I place the result in a register and return the control to the caller of the procedure. One important thing here is, how do we know from where to continue with my program? So for that, in LinkBI, what we have is a register which is X30, which is also called the link register. And in this register, automatically, without the programmer doing anything, once I call a procedure, the address of the next function is stored in that register. So when I return from a procedure call, LinkBI knows where to continue my program. Let me show you this with two more instructions, and then with an example. So for doing this, for calling a procedure and then returning the control back to the caller, we have two instructions. One is called BL, which means branch with link. So for calling a procedure, we will type this. We will use this instruction, BL plus the name of the procedure. In the example before, the name of the procedure was swap. So when we use this instruction, the instruction following the BL instruction will be put in register X30, as I have mentioned, the link register, which is the next instruction to do after I finish my procedure. And then after storing that value, it will jump to the procedure call. It will jump to the code where in the example below the swap function was. Once I finish my procedure, I need to use an instruction to return to the point to where it was called that procedure. In this case, we use the instruction BR, which means branch to register, and we put here register LR, which is the link register, which is actually the X30 register, which has been stored when I have called the procedure. And with that, I will continue with the following instruction. What happens actually is that this LR register, this address is copied to something called program counter. or PC, but we will come to this later. Right now, we are going to see an example to see if we can clarify this. So as I have mentioned, I'm going to call a procedure. So I use the branch with link instruction BL, and I'm going to call to a procedure. In this case, the procedure is called swap, but it could have any name, the name that the programmer has decided. So once I call this BL branch with link, what happens is the returning address. So once I finish the procedure, I will return to this address. So to this instruction. So I will this command BL will automatically store the next instruction, which is this one, in the register X30, which is the link register. And after having saved the next instruction to perform after the procedure, it will then jump to the procedure. Okay, so if I do a branch with link instruction, the BL instruction, before actually going to the procedure, this instruction stores the next instruction in this register, in the link register in X30, and then jumps to the procedure. We do what we need to do in that procedure, in this case swapping the values, and then I call the branch to register instruction in order to return back. In this case, we have branch to register, and the register is link register or X30, which what is going to do is going back to the instruction which is in the address of X30, the link register, which is actually the add instruction. Make sense? I'm going to repeat that again, okay, for you. So I'm going to call a function which is called swap. When I type this instruction BL, what happens is that before actually jumping to the swap function, to the swap procedure, the address of the next instruction is stored in a register, in a special register called link register. Then I jump to the procedure, I do whatever I need to do in the procedure, and when I want to return, I use the branch to register, and I'm going to branch to the address in the register link register, which is actually the following address after my call to the procedure. Make sense? This information of this link register, you can also find it here in the LegBI data reference. You see we have here the register X30, which is also called LR and which has the return address for a procedure. As mentioned, I have also put a PDF more clear here, which is actually saying what I have mentioned. Okay. Let me check if you have any question. Okay, someone is asking where are procedures used. So procedures, as I have mentioned, are you can see them as functions. They are used to make the code more readable and to make it have a better structure. Okay, so let me go back to what I was saying before regarding the program counter, or which is usually referred to as PC. I have mentioned you that what happens once I call the BR, the branch to register instruction, is that the content of the register LR is copied into the program counter. So what is the program counter? The program counter is a register with the address of the instruction in the program being executed. So remember that I have told you that we have the instructions in memory. So as we have the instructions in memory, those instructions have an address in memory. So the first instruction will be in a given memory address, the second instruction will be in another memory address, and so on. So what happens here is that in register LR, we have the next instruction to execute. And as we have jumped to a procedure and we want to return back, the program is not sequential. So in order to make this jump, we modify the value of the program counter. We modify the value of the next instruction to be executed. So let me show you with this example. So here we have, imagine that we have the memory. So we have those instructions in memory, the ones I have shown you in the previous example. We have the call to the swap procedure, which is defined here. We have also the return of the swap procedure, and this is the next instruction once the procedure has finished. For simplifying everything, imagine that the first instruction is in address 0 of memory, the next instruction is in address 4, and so on. So I have also placed here the value of the program counter. So when I'm executing this instruction, the value of the program counter is the address where this instruction is stored in memory, in this case 0. Usually, for regular instructions, for going from one instruction to another, I just add 4. Why I add 4? Remember, I told you that in LegVI, the instructions are 30 bits width. And remember that I have also mentioned that the memory is byte address. That means that every value refers to 1 byte, 8 bits. So with 4 positions, I'm referring to 32 bits. That's why one instruction has one address. It occupies 32 bits of the memory. So the next instruction will be in position 4, in address 4, because 4 multiplied by 8. So 4 multiplied by 8 is 32. Make sense? So then, coming back to what I was saying, I have my branch and link instruction, which is in address 0 of memory. Therefore, the program counter value is 0. And what happens when I call this instruction is that I store the value of the link register. I say, OK, once I came back from the procedure, the next instruction to be executed will be 4, which is actually the next one after the branch with link call. So I will call the branch with link instruction. I will store the next instruction to be executed in link register. I will jump to the swap procedure. I will do what I need to do. And when I'm here, I return the control. I branch to a register. So if I go to register link register, I will see, oh, the next instruction to perform is in address 4. So I go to address 4, and then what happens is that actually the program counter value is 4, and I continue with my program. Remember that, as I have mentioned, what we have here, it's just for making it simple. What happens in reality is that to be precise, we need to use hexadecimal values in order to actually represent the actual address of each instruction. Because with hexadecimal values, from 0 hexadecimal to 4 hexadecimals, we have actually the 32 bits. Okay, so this will be in hexadecimal the actual memory address. Okay, and from previous slide to this slide, the only thing which changes is that I'm using hexadecimal values just to be more precise, but the idea behind everything is similar. And remember that I have mentioned you that we have several registers. Once we call a procedure call, one we call a procedure. Some of those registers must be preserved. What this means? This means that if I call a procedure and I have a value before calling that procedure in a register, maybe that register is going to be overwritten by the procedure, and in some cases this register the value of that register will be lost. When that happens, for instance, when I use temporary registers, the value is going to be lost. That means that if before calling a procedure I have a value in a register, let's say register 9, that value could be lost. So I cannot rely on the value on register 9 once the procedure has finished. What should I do if I want to keep the value in a variable, in a register? So I need to use registers which are preserved after a procedure call. For instance, registers 19 to register 27 are which we call safe registers. That means that they are preserved on a procedure call. The same happens, for instance, with the link register, which is the place in which we have mentioned we store the return address. So what we have say here is that we have different registers which are preserved on procedure calls. We have mentioned that temporary registers are not preserved, and safe registers are preserved and must be preserved on a procedure call. And this is this must be done by the programmer. Okay, let me check if I see any question here, any interesting question. So someone is asking something regarding when I call a branch, is the address stored on a stack? So we will be mentioning the stack later. So and I will be addressing that point later. Someone is asking, using BRLR, will the address of the next instruction be stored again in LR? So no, remember that what we have seen is that in order to store something in LR, I need to use BL instruction. If I use BR instruction, the value of LR instruction is not modified. Okay, so when I use B and L branch with link, the value of LR is updated. But when I use branch to register, the value of LR doesn't change. Okay, it's consumed, but it doesn't change. It is not changed. Yeah, someone is asking also what happens to LR if you call a procedure within a procedure. So this is a very interesting question, and we'll be also responding this later. But see that the LR register is not preserved. So the programmer must preserve this. So what happens if inside a procedure I call another procedure? I need to store, the programmer needs to store the previous value of LR. Okay, someone is asking, what does calling a branch mean? It means calling a procedure. It means calling a label that I have in my program. We have seen this on labs and we have seen this in class. Okay, so here in this code, when I have a B here, when I have the branch, any instruction starting with a B will jump to something, to a label or to an address. In this case, it means that if I have branch and a label here, it will jump to this label. Okay, so we are going to follow from what we were. So now I have mentioned at the beginning that we have some registers that were used for inputting data to procedures or functions and also for results. So those registers are not preserved. That means that if I call a procedure, any value which is in those registers will be lost. So for instance, let's go back to the swap procedure. So imagine that we have the argument f is stored in the register 0 and the argument g is stored in the register 1. We then swap the values and then return the value to the caller. So once I return the value to the caller, the values in x0 and x1 are maybe different from the ones they have before calling that procedure. With this is what we refer as the values are not preserved on code, that they can change. So now someone was pointing this in the questions. What happens if we need more registers for parameters? What we are doing, what we need. So what we are going to do is, as someone have mentioned in one question, using a kind of stack. So we will store the registers we are currently not using in memory, and then we have a structure there which is called a stack, and where we can which we can use for using additional registers. We have a pointer, let's say a register, which tells us what is the most recently allocated address in the stack, in order to know where is the last element we push to that stack. So in order to add elements to the stack, I just push that element, and when I want to remove to the stack, we will use the term pop. And as we see here, the stack grows from higher to lower addresses, and we will explain the reason for this later. Someone is saying, is the preserved thing similar to global and local variables? Yes, you could see it like that. So when you are in a program, you could see like everything in the registers x19 to x17, you could see them as global variables, and then the temporary registers and the argument registers you could see as local variables to the procedure. Yeah, that could be a very good way of saying that. So let me show you an example of how this stack works. So here in the beginning, imagine that in our stacks, in the stack, we only have the contents of one register, register x20. Here, as we see, we have the addresses in hexadecimal. So each address here differs from the previous one in 4. Why in 4? As I have mentioned, because each address points to 32 bits. So as registers are 64 bits, so we need to use 2 addresses. So initially our stack pointer points to this address, and we have only one register, x20. Imagine that now that I'm going, I want to push another element to the stack. So then my stack pointer increases in 2 addresses because, well, in 4 plus 4 addresses, because I'm inserting another register which has 64 bits. Okay. And then imagine that I want to remove this register, x19. I don't need it anymore. So then I just, for removing it, I just put the stack pointer to the address of the previous register, which was x20. Okay, so initially I have register 20, then I have added a register 19 and updated the stack pointer, and after that I have removed the register 19 and the stack pointer was restored. Okay, let me show you this with an example with real legBI code. So I have, again, I'm calling a procedure, the swap procedure. So initially, I know that I'm going to use two registers, 20 and 19. So the first thing I do is, okay, I adjust the stack pointer. So if I want to add two elements, I will need to increase the pointer by 16. Why? Because each register is 64 bits. And the memory is byte address. So 8 multiplied by 8 is 64. So I need to add 8 for each register. This is the same, similar to what we mentioned when working with arrays in previous lectures. So then I modify the stack pointer, which is just doing this. So the stack pointer is now pointed to this address after doing this. Okay. Now I store the value of 20 on the stack with the start function instruction we have already seen. Okay, and then the next instruction I do the same with the register 19. Okay, so I have everything stored in my program. I have all the variables that must be preserved stored in the stack. Now I can modify them if I want in my program. So here in my program, I can do whatever I want here. And in this case, I'm swapping the values. And before returning the control, I need to restore the values of x20 and x19. Why? Because the caller may be using those registers, and legBI tells us that those registers must be preserved on a procedure call. So I have mentioned, we have seen that here it says that registers from 19 to 27 must be preserved on a procedure call. So that's why we are storing those registers in the stack, doing what I need to do with those registers, and then restoring them back. For restoring them, what I do? I load the value of pointed by the stack pointer at that position in register 19. I load the value of the stack pointer with the register 20, and then I restore the stack pointer. So graphically will be, so I have load the value here in register, if I remember well, it was register 20, then the value here in register 19, and then I restore the value of the stack pointer. Okay, so we have here this, in another example, we have here this graphically. So this is the status of the stack pointer before calling the procedure. So the stack pointer points at any place, I don't mind. Once I call my procedure, what happens is that I store in the stack the registers I plan to use and that must be preserved on a procedure call. And once I finish the procedure call, I restore the stack pointer and I remove those elements. I restored also the value of those registers. Make sense? Let me check if you have. So BL and BR, someone is asking if they are registers. No, though they are instructions. BL is branch with link and BR is branch to register. Those are instructions, operation codes for instructions. They are not register. Preserve on call means, someone is asking, what does preserve on call mean? Preserve on call, when you see, let me show you. When you see here, preserve on call, it means preserve on a procedure call. It means that are those registers, the content of those registers is going to be the same once I call a procedure and the procedure return back. So if here we have a no, it means that the value in any data, the content of those registers will be could be overwritten in a procedure. But if I have that yes, that the values are preserved, it means that if before calling a procedure, I have something in register 19, after calling the procedure, that value will be preserved and will be the same. When I mention, someone is asking what is a parameter in general. So when I mention here a parameter, I mention an argument, an input argument of for a procedure. You could it could be similar to an input argument for a function. Someone is asking if the stack space is allocated to the program from memory by the operating system during execution. We will see something regarding this later. Yes, let's say that we have a space there which is for our program and which can be dynamically used by us. Someone is asking, is a procedure similar to a class then? I will not say to a class. It will be similar to a method of a class. Someone is asking if the stack is similar to that of the first in last out thing. So is the other way is called LIFO, last in first out. So someone is asking if there is a direct push and pop instruction like in 8086. No, the programmer must do it by using the store and load instruction. Someone is asking why in the previous example, in the example we see now in the slide, why register 19 is below 9 and 10 for any particular reason, okay? Is that the programmer decided to write them in that way. And finally, in this slide, for instance, someone is saying if the SP, the stack pointer points to register 19 because it was the last added used. Yes, the stack pointer points to the last register added to the stack. Okay, so let's continue then. So here I have something for you. So keep in mind this. Keeping in mind this slide. So what do you think? Do you think that the contents of the register 10, register 9, and register 19 are correctly here in the stack pointer? I mean, are those registers need to be preserved on a procedure call? What do you think? So from what we have seen here, so do you think that we need to restore to save the registers to preserve the contents of those registers? So I'm going to make to put an announcement here, and if you do thumbs up, it means that you agree with the claim I'm making here. For instance, the first claim is yes, we need to preserve x10. Okay, so thumbs up means that you are agree with that. And now we and the other way will be that we don't know. I'll give you some time. Okay, I see that we don't need to preserve register 10 is growing quickly. So why it does not need to be preserved? Because as I have shown you here, register 10 is a temporary register and must not be preserved. Okay, so then we should not be doing this because that register, the content of that register should not be preserved. Okay, so now if I ask you the same for register 19, I have added an announcement here, again following the same. Okay, in this case, as you are properly reacting to my message, so you are right, this register does not be must not be preserved because must be preserved because we have seen here that register 19 must be preserved on a call. So you are right, it must be preserved and it's correctly placed here. Okay, so here I have just you have here an example showing this. So in this case, I'm assuming that the example was right, and for any reason the programmer wants to save the register 10 on the stack. So we adjust the stack. In this case, we are going to add 3 items. We need to increment by 8 for each item. So we store all those items in the stack. We do what we want to do in the procedure, and before ending, we restore the value of those elements into from the stack into the memory. Okay. So this is what I have actually asked you, and this is the answer. So we don't need to preserve the value of 9 and 10, but we need to preserve the value of 19. This is what we have just been discussing. So apart from the stack, we have also a space for a procedure in order to store. Imagine we need a space for additional arrays, additional structures. There is a place for this, which is called procedure frame. And this procedure frame is a segment in the stack which is available for us, as someone of you was pointing before. It's available for us for storing safe registers, local variables, and any other structure that I need to use for my procedure. Apart from the stack pointer, which points to the last element added to the stack, we have a new element, the frame pointer, which points to the first address what can be used in my procedure. For instance, till now we only had this stack pointer, which pointed to the last element used from my stack, and now what we are adding is the frame pointer, which points to the first element of my procedure frame, of the space available in my procedure for extra space. So for instance, here, as I have mentioned, I can use it for saving registers I must preserve, and I can also create local arrays or extractors if I need any of that to use in my program. Okay, so in the end, in the memory, what we will have is lower addresses are usually reserved for the operating system and so on, but then on the top of this we will have a section called text, which contains the program code, and the program counter points to the first instruction which is here in my program code, the first instruction to be executed. On top of that, we have what we call static data. Someone was mentioning before global variables. So this is what we store here, something that don't change in all my program. And then we have the dynamic data. So the stack that we have been talking about is will be growing from higher memory addresses to lower memory addresses, and we have a new thing here, dynamic data, which is something which we use in C or in Java in order to dynamically allocate space for structures and arrays. So, and we have also mentioned that we have this stack pointer and the frame pointer. So when we move, when we do assume to this space, to this stack and dynamic data space, so what we have is something like this. We have a space for extra space for our procedure. The first address of that space is pointed by the frame pointer, and the last address is pointed by the stack pointer. So all this space is available for my procedure. Okay, so we have seen procedure calls. I know that this can be a bit confusing in the beginning, but don't worry, it will be more clear in the next lab and also in the next lecture. The next lecture we will be seeing something called pseudo instructions. We'll be also speaking about addressing modes, and we will be also seeing compilation and execution flow in computer architecture. So let me see if I see an interesting question in those. So someone is asking, is it dangerous if you don't preserve a register that must be preserved? Of course, the program will not function as expected, and that will be a bug, and that will be a problem of the programming. Someone is asking, why would we put save registers in a stack if they are already preserved on call? When I say here that something must be preserved on call, it doesn't mean that it is automatically preserved. It means that the programmer is responsible from preserving this on a call. And that's why we need to, if we have here a yes in the procedure, we need to store it in the stack and actually restore it. And then someone is saying, are stacks used to preserve register data that could not be preserved on a call? Yes, that's precisely what I was trying to say now. So someone is asking regarding frame pointer and stack pointer. So the frame pointer points to the first element, to the first address of memory, which is available in my procedure, which is available for storing data in my procedure. And the stack pointer points to the last address I have used in my procedure. So you need to see this, remember, this is a higher memory address and this is a lower memory address. So this grows in the opposite direction as the one you expect. Why? Because all this data in memory is already used. So, and what is not used is that one. So we know the higher address, and we this is increasing down, and with that we can allocate dynamic data from lower memories to higher memories, and at the same time we can allocate stack data from higher memories to lower addresses. And with this we will the management of this dynamic data is more performs better. Okay, so I hope you have understood something today. I know that those think of procedure calls in assembly language. This is a very lower program concepts. Those are very low program concepts. So you will need more a bit of time in order to fully understand this, but step by step. So we will manage to do it. Remember that in the first lab, all we learn in the lectures, we use the lab in order to support those lectures. And what we will do in the next lab is also doing similar things. We will try to do things in order to support all we say in all the lectures. So as always, remember that if you have additional questions, you can use the ticketing systems from the school, and we will try to help you as much as possible. So thank you very much for listening. Hope you have a nice rest of the day, and see you tomorrow. Thank you very much for your attention, and yeah, bye, goodbye, see you, thanks.